Hello, everyone. So, we're going to talk about conservation of energy, and we're going to focus our calculations around mechanical energy. And we've discussed two main types of mechanical energy, the first being kinetic, the second being gravitational potential. So we have our kinetic energy, which is 1/2 mass velocity squared, okay? So that's our base equation for kinetic energy, and then we have potential energy. We'll have potential energy, which is m mass acceleration due to gravity, and then the height of the object, okay? And how conservation of energy works is it's saying if we add up all the energy that we start with, then that better equal all of the energy that we end with. Whatever we start with, we end with. And again, like I said, we're going to focus on kinetic and potential. And so if you want, after you make the step, you can go in and you could say kinetic energy initial plus potential energy initial has to equal kinetic energy final plus potential energy final. And then from there, evaluate what's going on. If in the initial condition we don't have a velocity, if velocity is 0, then we wouldn't have any initial kinetic energy. Same thing for the final. If the final condition, the object doesn't have any velocity, then it doesn't have any kinetic energy. And then height is the component that we're going to be focusing on and trying to identify for potential energy. If it starts out on the ground and the height is 0, then it wouldn't have any initial potential energy. But then if it's raised up onto a shelf and now it has height for the final condition, then we would have potential energy final. So start each one of these conservation of energy questions by drawing the initial and the final, then writing out the conservation of energy equation and determining what you're starting with and what you're ending with. And then after that, go through and plug in the equations for these values. Usually from there, you can see if mass cancels, or you can identify, what you're solving for, and you can rearrange that equation. Okay, now, like I told you, we're going to focus on gravitational potential energy, but there are a few other types of potential energy. We have elastic potential energy. If you stretch anything that's compressed, like a spring, or you pull back, you're drawing a bow, you're creating potential energy. Chemical potential energy, think of this as fuel, I think is like the ideal way of visualizing this. Just like fuel that we put into our body, those carbohydrates, they break down, they form energy, or the fuel we put into cars or anything else. And then gravitational potential, the one that we're focusing on. Example number 8. What is the potential energy of a car at the top of a 30-meter hill? It has a mass of 890 kilograms. Okay, so potential energy is just asking for the potential energy. We know potential energy is mass times by acceleration due to gravity, which we're just calling g right now, times by h. And so we have a mass of 890 kilograms. Acceleration due to gravity, 9.81 meters per second squared. And then height, 30 meters. Okay. Let's see, let me grab a calculator. Okay. So 890 times by 9.81 times by 30. Okay, we have a big number here. 2,61927, and then I want us to recognize units, kilograms, meters squared per second squared, gram. Okay, sig figs, 3 sig figs across, so we would have 262. Okay. And then final units, well, a kilogram meter squared per second squared is just a joule. Okay, we saw this when we were talking earlier about energy and work, units of joules. Okay. The kinetic energy of a moving object is equal to the work required to bring it to that speed. Okay, so what we're saying here is we have this work energy theorem that whatever work we have will result in an equal change in energy. If we supply work to an object, we increase its energy by the same amount of work that we applied. Okay, we know that work, another equation for work is force being applied over a displacement or a distance, and then change in, this was specifically kinetic energy, but let's write off to the side here. Work is equal to a change in energy. So this is the case for this particular situation, but anytime we change energy, work was done, or vice versa. And it doesn't have to be kinetic energy, it could be potential energy as well. Okay. So how fast is a car going if it has kinetic energy of 12,000 joules with a mass of 890 kilograms? How fast is the car going? Okay, so we didn't have the kinetic energy and we have the mass. Well, kinetic energy is equal to 1/2 mass velocity squared. And we want to know how fast the car is going. So we know mass, we know the kinetic energy. Let's rearrange this equation to solve for velocity. So I'm going to start by dividing by m and 1/2. Okay. Now, you can write this either way. You could do 1/2 on the bottom, or you could have 2 on the top, same thing. Okay. And that equals velocity squared. And so we'll take the square root of both sides of that equation. Okay. And now I'm going to plug in some numbers. So square root, and then on the top of my fraction here, 2 times by the kinetic energy, which is 12,000. Okay. And then divided by the mass, which was 890. 5.2 sig figs, 2 sig figs, so 5.2 meters per second. Okay. Now, let's see. We know that's supposed to be meters per second because it's a velocity, but let's do, where are we at time-wise? Yes. Let's do a unit analysis to double check this. So we have kinetic energy, 2 is unitless, kinetic energy, which is a joule, divided by mass, which is kilograms, and then everything square root. So let's start here. A joule divided by kilograms. Okay, so that would be a joule, which is a kilogram, meters squared per second squared, divided by a kilogram, which is the same as multiplying by the inverse, right? So kilograms cancel. So we're left with meters squared per second squared, but everything's in a square root. So if we take the square root of that, then we have meters per second. So we did, in fact, end with the units that we were wanting. So that must mean we rearranged our equation correctly. Okay, so this is basically what we were talking about before with the conservation of energy. Okay, it's this idea right here, and it's recognizing what's happening in a situation. So let's look at 2 different situations. Let's say that we have a ball on a table, and then it's like right on the edge, and then it just rolls off, and eventually it's going to hit the ground. Okay, so initially the ball is just barely like leaving the table, and then the final condition is that it hit the ground. Okay? So this would be initial, and then we have our final, right? The ball's down there. Okay, on the ground. So we could also think of it as like the moment right before it hits ground. Let's see if I can get this to focus. Now, initially, let's say some of the energies initial need to equal some of the energies final. And let's just plug in our kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. So initially, we don't have any velocity. It's like that moment right before it falls. And so if we don't have velocity, then we don't have kinetic energy, right? Because kinetic energy is 1/2 mass velocity squared. So anything multiplied by 0 is 0. We do have some height above the ground, so we do have potential energy. Right before we hit the ground, like the very moment right before, we do have a velocity, so we would have a kinetic energy, but we'd no longer have a height, because potential energy equals mgh. That height is essentially 0, so we don't have any potential energy. And so then we could say the potential energy initial is going to equal to all the kinetic energy final. And at that point, I plug in what I know. That potential energy is mgh, and that kinetic energy is 1/2 mass. This is a final squared. Okay, so that's the first steps that I would take to a problem that has an approach like that. Now let's think of another situation. Okay, what if we have a ramp? Okay, so we have this ramp, and we have a ball that's starting at the bottom of the ramp, and it's going to have some initial velocity, okay? And that when it gets to the top of the ramp here, we'll make it kind of more curved. So like when it gets to the top here, it doesn't come to a stop. It's got a smaller velocity, but it's still going, okay? So this is the initial. This is a final. So sum of the energy initial will equal sum of the energy final. Initially, well, let's plug on the kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. Okay, so once I have this written out, now I'm going to determine what I have in both situations. Are any of these 0? Because that'll help clean up the work here. So initially, I have a velocity, so I do have an initial kinetic energy. Initially, I'm kind of at this ground level. I don't have any height, so I wouldn't have any initial potential energy. On the other end, I do have a small velocity when I reach my final conditions here, so I would have a kinetic energy final. And I am up above the origin, above where I started, so there is a height component, so I would have potential energy final. So this one would be kinetic energy initial equals kinetic energy final plus potential energy final. So I'd have 1/2 mass velocity initial squared, which equals 1/2 mass velocity final squared plus mgh. Okay, a little hint for you guys in any of these kind of situations. If we're not solving for an energy in its entirety, like if I'm not asking for kinetic energy initial if this and this is given, if I'm asking for something within that energy like a velocity or a height, then most of the time, the mass cancels, because look, we have mass in every single component here. So we could divide by m on both sides of the equation and mass would cancel. And same thing over here, we have mass on